Earth hasn't always been such a peaceful place. Over its 4.5 billion year history, our planet has been struck by catastrophes of such magnitude that they make any Hollywood apocalypse look like a children's fairy tale. 5 times, life on Earth has come close to the very brink of destruction. 5 times, almost all life has vanished from the face of the planet. And each time, it wasn't the strongest or the smartest who survived, but simply those lucky enough to be in the right place at the right time. We are the descendants of these lucky ones, those few organisms that survived the icy hell, acidic oceans, and firestorms. But something new is happening now. The sixth mass extinction has already begun, and for the first time in the planet's history, one species has the power to stop it or speed it up. We have a finger on the button, and we decide every day whether to press it or not. Before we delve into this story of survival and disaster, please subscribe and like the channel so you don't miss other mysteries of our planet that we uncover each week. Now let's take a journey through millions of years and discover how Earth has died and been reborn again and again. When you look at the green forests, blue oceans, and endless diversity of life around you, it seems as if it has always been this way, as if our planet is a safe home, a stable cradle in which life has evolved smoothly and without much disruption. Biology textbooks paint a beautiful picture of evolution. The first vertebrates emerged from the water, then dinosaurs, then mammals, and then us. It all looks like a logical chain, with each link following from the previous one. But this is an illusion. This appearance of stability is deceptive, like the calm surface of the ocean before a tsunami. In reality, the history of life on Earth is not a smooth ascent up the ladder of progress, but a series of desperate leaps between catastrophes. Imagine a game where every few tens of millions of years someone hits the reset button and erases almost everything that came before. That's the true history of our planet. For a long time, scientists weren't even aware of these catastrophes. In the 19th century, paleontologists discovered fossils of ancient creatures and observed that one species replaced another, but they thought this happened gradually. Charles Darwin and his followers believed in slow evolution, where changes accumulate gradually over generations. The idea of sudden global cataclysms seemed absurd to them, something out of the realm of biblical myths about the Great Flood. Science sought to explain the past through processes we see today: erosion, sedimentation, the gradual extinction of less adapted species. No one wanted to believe that the planet could suddenly turn into hell. But then, in the 20th century, strange data began to accumulate. Geologists discovered thin layers of clay in ancient rocks that separated one era from another. Below this layer, the fossil record contained a huge diversity of species, and above it, almost nothing. Entire families of organisms simply disappeared from the rock record. At first, this was attributed to the incompleteness of the geological record, with the necessary rocks simply not having been preserved. But the more they dug, the clearer it became. The extinctions were real and almost instantaneous by geological standards. Over the course of tens or hundreds of thousands of years, and sometimes even faster, millions of species were wiped from the face of the Earth. This wasn't a gradual extinction of the weak, it was a massacre. The first scientist to seriously discuss mass extinctions was the American paleontologist John Phillips, back in the mid-19th century. He studied fossils and observed that Earth's history can be divided into large time blocks, ending with sharp breaks in the diversity of life. He called these blocks the Paleozoic, Mesozoic, and Cenozoic eras. The boundaries between them coincided with the moments when most known species suddenly ceased to be found in younger breeds. But Phillips' colleagues didn't take his ideas seriously. They were too revolutionary, too catastrophic. The science of the time favored smoothness and gradualism. The situation changed only toward the end of the 20th century, when new dating methods and more accurate data emerged. Soviet paleontologist Dmitry Roshin and American paleontologist David Robb independently analyzed extinction statistics over the past 500 million years. They plotted graphs showing how many families of organisms were disappearing at any given moment. and the graphs were terrifying. Most of the time, the line was relatively flat, with only minor fluctuations, but then, at certain points, it would spike like a feverish patient's temperature. These peaks meant that tens of times more species than usual went extinct in a short period of time. Robb called these events mass extinctions and identified 5 major ones, which were so devastating that they forever changed the face of life on the planet. The Big Five, as they came to be known, occurred at the end of the Ordovician period 445 million years ago, in a late Devonian 375 million years ago, at the Permian Triassic boundary 252 million years ago, at the end of the Triassic 201 million years ago, and at the Cretaceous-Paleogene boundary 66 million years ago. Each of these events wiped out between 70 and 96% of all species. Think about it. 96%. Almost all life on the planet was wiped out. If the same thing happened today, only 4% of the millions of species of plants, animals, fungi, and bacteria would remain. Cities would be abandoned, forests would become cemeteries, and the oceans would turn into dead deserts. And this isn't fantasy. These are real events from Earth's past. When scientists realized the scale of these catastrophes, an obvious question arose. What could have caused them? What force could have killed almost all life on an entire planet? The first hypotheses were simple. Perhaps it was the ice ages. Indeed, a cold snap could kill off many species, especially those adapted to warmer climates. Alternatively, a sharp warming could occur. If temperatures rise too high, the oceans will warm up, the oxygen in the water will decrease, and marine organisms will begin to suffocate. Both ideas sounded logical, but questions remained. Why were these climate changes so abrupt? What could have cooled or warmed the entire planet so quickly? Some researchers suggested an extraterrestrial cause. What if giant asteroids or comets had struck Earth? The impact of a celestial body, several kilometers in diameter, could have caused tsunamis, earthquakes, and thrown so much dust into the atmosphere that the sun would have been obscured for months or years. Plants would stop photosynthesizing, temperatures would drop, and food chains would collapse. This idea seemed too dramatic until 1980, when geologist Luis Alvarez and his son Walter discovered a thin layer of clay enriched in iridium in rocks at the Cretaceous-Paleogene boundary. Iridium is a rare element on Earth's surface, but it is abundant in asteroids. The Alvarez family's discovery was a sensation. It proved that at least one of the mass extinctions, the one that killed the dinosaurs, was caused by an asteroid impact. The impact crater itself was later found in Mexico, near the Yucatan Peninsula. It was called the Chicxulub crater, and its diameter exceeded 180 kilometers. But asteroids couldn't explain all 5 great extinctions. No evidence of cosmic impacts was found for the other catastrophes. So, the causes were terrestrial. And this is where volcanoes came into play. Not ordinary volcanoes that occasionally erupt and spew lava and ash, but something far more terrifying: traps. These are gigantic igneous provinces where lava flows from cracks in the Earth's crust and floods vast areas, sometimes covering millions of square kilometers. Such eruptions last not days or months, but hundreds of thousands of years. During this time, monstrous volumes of carbon dioxide, sulfur, chlorine, and other gases are released into the atmosphere. First, sulfur and ash cause cooling. Then carbon dioxide accumulates and causes a powerful greenhouse effect. Temperatures fluctuate, the climate becomes unpredictable, the oceans acidify, and oxygen levels drop. Life is crushed. And the most terrifying thing is that such eruptions coincide with several of the great extinctions. The Siberian traps, the Deccan traps, the Central Atlantic traps. Each of these provinces is associated with one of these catastrophes. It turns out that Earth killed its inhabitants in different ways. Sometimes it was ice, sometimes fire, sometimes a strike from the sky, sometimes a slow poisoning of the atmosphere and oceans. But the mechanism was always the same: a sudden change in conditions to which life had no time to adapt. Evolution works through natural selection, and selection takes time. It takes generations for beneficial mutations to spread throughout the population. But when climate change takes tens of thousands of years or less, there's no time. Species go extinct not because they're weak, but because they can't keep up. Imagine living in the tropics, and suddenly the temperature drops by 20 degrees Celsius over the course of a few thousand years. Your body is adapted to the heat. Your food grows in a warm climate. Your predators and parasites thrive in warmth. And then suddenly, all of this disappears. You may be the strongest and smartest organism in your ecosystem, but if your ecosystem collapses, you're doomed. Modern science has confirmed that mass extinctions are not myths or accidents, but rather natural events in Earth's history. The planet is a living system, breathing, moving, and changing. Continents drift, oceans open and close, mountains rise and fall. All these processes influence the climate, ocean currents, and atmospheric gas levels. And from time to time, these changes interact so unfavorably that the result is catastrophic. Life on Earth balances on a fine line between order and chaos. Most of the time, the balance is maintained and species thrive. But occasionally, the balance is upset and extinction occurs. And then, when the catastrophe ends, life regenerates from the handful of survivors and flourishes once again, filling the vacated ecological niches. This cycle of death and rebirth is the true history of our planet. Let's now travel back in time to the end of the Ordovician period, 445 million years ago. The Earth then looked very different from how it does today. The continents were arranged differently, the climate was different, and life existed almost exclusively in the ocean. The land was deserted and lifeless, with only a few primitive, moss-like plants growing on the shores. All the diversity, all the beauty, all the complexity of life was concentrated underwater. Trilobites, ancient relatives of modern crustaceans and insects with segmented shells, swam in the Ordovician seas. They crawled along the bottom, burrowed in the seabed, and hunted small prey. Brachiopods, bivalves similar in appearance to mollusks, but with a completely different structure, lived alongside them. Their shells littered the seafloor, filtering the water and catching food particles. The coral reefs, built not by corals, but by other organisms like tabulates and stromatophorates, were teeming with life. Feather-like graptoliths drifted through the water, forming entire colonies. And above them all reigned the eurypterids, predators up to 2 meters long, with pincers and segmented tails. They were the apex of the food chain, the rulers of the Ordovician seas. This world was thriving. The Ordovician period is known as the Great Ordovician Radiation, when the diversity of marine life reached unprecedented levels. The number of organism families tripled in just tens of millions of years. The oceans teemed with life. The ecosystems were complex and resilient. It seemed as if nothing could disturb this splendor. But in reality, deep within the planet, processes were already underway that would lead to the first of the great catastrophes. At the South Pole lay the gigantic supercontinent Gondwana, encompassing South America, Africa, India, Antarctica, and Australia. This continent was slowly drifting southward at a rate of a few centimeters per year. Tectonic plates were shifting, and Gondwana was sliding toward the pole. This movement seemed insignificant, but it set the stage for the apocalypse. When a large land mass moves over a pole, the climate begins to change. This is because land reflects sunlight much better than the ocean. And if ice forms on land, the reflection becomes even stronger. This is called albedo, the surface's ability to reflect light. The higher the albedo, the less heat is absorbed and the colder it becomes. Gondwana, once at the pole, became a cold trap. The snow that fell in winter didn't melt in summer. It accumulated layer after layer and gradually turned to ice. The ice sheet began to grow, slowly at first, then faster and faster. A positive feedback loop began to take effect. The more ice, the more light is reflected. The colder it gets, the more ice. In a matter of 1,000,000 years, maybe less, an ice shell kilometers thick formed on Gondwana. It was a full-blown ice age. A cold snap hit the oceans, dropping water temperatures by several degrees, which was critical for marine organisms that couldn't regulate their body temperature. Many species, especially those living in warm tropical waters, began to die out simply from the cold. But that was just the beginning. The main problem came from an unexpected source. When glaciers form, water is trapped within them as ice. Sea levels are starting to fall, and they've been falling fast. Over the course of several 100,000 years, global sea levels have dropped by more than 100 meters. Imagine the loss of 100 meters of water. All the shallow waters and shelves where most life was concentrated were exposed. Coral reefs that grew at depths of tens of meters suddenly found themselves on dry land. They dried out in the sun and turned to stone. The shallow lagoons where the young fish bred and grew disappeared. The entire shelf ecosystem, the most productive part of the ocean, was destroyed. But that's not all. As sea levels fall, the coastline retreats. The continental shelf, the broad, shallow platform surrounding the continents that occupied vast areas during the Ordovician, suddenly became dry land. After all, it was on the shelf that brachiopods, trilobites, corals, and most other organisms lived. They couldn't migrate to the deep ocean. The conditions there are different with different pressure, different temperatures, and different food sources. They simply died on the spot. Paleontologists are finding massive accumulations of fossils in late Ordovician rocks, entire cemeteries of what were once living creatures. These organisms didn't have time to evolve, didn't have time to meridianize. They simply disappeared. And to top it all off, ocean currents changed. Cold water from the poles began to sink and flow toward the equator, displacing warmer water upward. This is called the thermocholine circulation, and it plays a vital role in the distribution of oxygen and nutrients in the ocean. But when the climate changes dramatically, this circulation can be disrupted. At the end of the Ordovician, this is exactly what happened. Deep waters stopped mixing with surface waters. The oxygen supplied to the water from the surface atmosphere did not reach the depths. Meanwhile, organic matter, dead plankton, excrement, and plant debris sank to the bottom and began to decompose. The bacteria that decomposed this organic matter consumed oxygen, and anoxia, or oxygen-free zones, began to grow in the ocean depths. Initially, these were small patches, but they gradually expanded. Anoxic zones, like black spots on an ocean map, crept upward, encroaching on ever deeper depths. Only a handful of specialized bacteria can survive in oxygen-deprived water. All the rest suffocate. Trilobites, which had previously thrived, began to die out en masse. Of the more than 60 trilobite families, only about 20 survived. Brachiopods lost almost half their diversity. Graptolites, which drifted through the water column, disappeared almost completely. Entire groups of organisms that had existed for tens of millions of years were wiped off the face of the earth. Scientists estimate that about 85% of all marine species became extinct at the end of the Ordovician. This means that out of every 20 species of life in the ocean, only 3 survived. The remaining 17 disappeared forever. What saved those few that survived? Luck. Pure, undeserved luck. It wasn't the strongest or the smartest who survived. Those who survived were those who happened to be in the right place. For example, those species that lived not on the continental shelves, but in deeper waters where the sea level didn't drop as dramatically. Or those who could tolerate low temperatures because their ancestors once lived in cool waters. Or those who didn't need much oxygen because their metabolism was slow. This is called pre-adaptation. The organism has some characteristic that wasn't useful before, but suddenly became useful when conditions changed. And this characteristic saved its life, even though it wasn't intended. This is how evolution works in times of catastrophe. This isn't a struggle for survival. It's a lottery. The Ordovician extinction ended as suddenly as it began. Several 100,000 years later, the glaciers on Gondwana began to melt. The climate warmed, sea levels rose, and the continental shelves became submerged again. Ocean currents recovered, and oxygen returned to the deep sea. Life began to recover. Surviving species, freed from competition from the extinct, began to reproduce and evolve, filling empty ecological niches. Within a few million years, the oceans were once again teeming with life. But this was a different life. Those who dominated the Ordovician had disappeared. New organisms took their place. The catastrophe reshuffled the cards. And this became a pattern. After each mass extinction, the biosphere was rebuilt. Old dominance faded, new ones arose. And no one could predict who would emerge victorious. About 70 million years passed after the Ordovician catastrophe. The Earth healed its wounds, life flourished again, and by the middle of the Devonian, the oceans were teeming with fish. It was during the Devonian that fish made an evolutionary breakthrough. They developed jaws, their fins became stronger and more flexible, and some learned to breathe air. This was the time when vertebrates began to conquer the planet. The first tetrapods, the Triassic and Extinction, were already crawling onto land, though they still spent most of their lives in the water. But the main event didn't take place in the ocean. It took place on land. Plants emerged from the water and began to colonize the continents. Before Devon, the land was almost empty. Yes, there were bacteria, fungi, and perhaps some primitive lichens and mosses, but there were no true plants with roots, stems, or leaves. But in Devon, everything changed. The first vascular plants appeared, with tissues for transporting water and nutrients. They could grow taller, capture more light, and compete with each other. And most importantly, they developed roots. Real, deep roots that penetrated the soil, broke up rocks, and sucked out minerals. It sounds harmless. Well, roots, big deal, but these roots changed the planet. Imagine the Devonian landscape. Just 100 years ago, it was simply bare rocks, deserts of stone and sand. And now, forests grow on these rocks. Tall, tree-like ferns, archaeopterids, horsetails, and club mosses have roots that penetrate the soil like a network. These roots secrete acids that dissolve minerals in rocks. They break down rocks, turning them into soil. The soil thickens, plants grow even better, and roots penetrate even deeper. It's a positive feedback loop, a self-reinforcing process. And it seems wonderful. Life is conquering the land, green forests are covering the continents. The air is becoming more oxygenated because plants are photosynthesizing. A triumph of life, isn't it? But this triumph had a dark side. When roots break down rocks, they release phosphorus and nitrogen. These elements are essential for life and form the basis of all proteins and DNA. Under normal conditions, phosphorus and nitrogen are in short supply in nature, limiting the growth of living organisms. But when the roots began to grind the rocks, phosphorus and nitrogen flooded the environment. Rain washed them into rivers, and the rivers carried them to the ocean. And an explosion of life began in the ocean. Algae and cyanobacteria, which had previously been growing slowly due to a lack of nutrients, suddenly found themselves in abundance. They began to reproduce at a frantic rate. The water in coastal areas turned green and red from the abundance of microorganisms. This is called an algal bloom or eutrophication. You may have seen this phenomenon in polluted lakes and rivers, where the water becomes murky and foul-smelling. The same thing happened in the Devonian oceans, only on a planetary scale. Algal blooms, at first glance, seem good for the ocean. More plant biomass, more food for herbivores, more oxygen in the water. But in reality, they're a disaster. Because all these algae, which have multiplied so rapidly, die after a while. Their bodies sink to the bottom and begin to decompose there. Bacteria pounce on this organic matter like a feast. They reproduce, eat, and breathe. And breathing consumes oxygen. The more organic matter that falls to the bottom, the more bacteria there are, and the more oxygen they consume. And at some point, the oxygen in the bottom waters runs out. Anoxia sets in. Anoxia spread from the coast into the ocean's interior. At first, these were small dead zones, but they grew. Fish, trying to save themselves, swam into the open ocean, but oxygen starvation set in there too. Imagine you're a fish swimming in the water, and suddenly you start suffocating. You rise to the surface, where there's more oxygen, but millions of other fish are already swimming there, all trying to breathe. The water at the surface boils with their movements. And then, even at the surface, there's not enough oxygen. And you die. Not from predators, not from disease, but simply from suffocation. Your body sinks to the bottom, decomposes, and makes the anoxia even worse. Death begets death. The Devonian extinction was not a single event like the Ordovician. It was a series of impacts spread over several million years. Scientists identify two major extinction pulses, one at the end of the Frankian, the other at the end of the Permian. Each time, entire groups of organisms disappeared. Coral reefs, which had flourished in the early Devonian, became almost completely extinct. Trilobites, already suffering during the Ordovician, lost even more families. Placoderms, the armored fishes that had been at the top of the food chain, disappeared. In total, about 75% of all species perished. This isn't as many as in the Ordovician, but it's still a monstrous figure. 3/4 of all life on Earth simply ceased to exist. The irony is that the culprits of this catastrophe were plants. The very plants that created soil, oxygenated the atmosphere, and made land habitable, poisoned the ocean with their fertilizers. This is the first known instance in Earth's history where living organisms created a catastrophe for themselves. Not an asteroid, not volcanoes, not glaciers, but life killed life. And this is a terrible lesson. It shows that the success of one group of organisms can spell doom for another. That an evolutionary breakthrough in one ecosystem can destroy a neighboring one. And that the Earth isn't a harmonious system where everything is balanced. It's a battlefield where the survival of some means the death of others. Plants, of course, aren't to blame. They had no malicious intent. They were simply doing what evolution dictated. They grew, multiplied, and conquered new territories. But the consequences of their success were catastrophic. And here it's important to understand one thing. There is no justice in nature. There is no reward for good behavior and no punishment for bad. There is only cause and effect. Plants released phosphorus. Phosphorus caused eutrophication. Eutrophication led to anoxia. Anoxia killed millions of species. A simple mechanical chain. And no one cares that the plants didn't want it. After the Devonian catastrophe, life returned. But the oceans were never the same. The coral reefs built by tabulates and stromators disappeared forever. They were replaced by new reef builders, modern corals that still create barrier reefs in the tropics. The armored fishes became extinct, but their place was taken by sharks and bony fishes, which proved more flexible and adaptable. Life found a way to continue, but she paid a terrible price. And something even more terrifying lay ahead. The Permian period began 290 million years ago and ended 252 million years ago. It was a time when all the Earth continents merged into a single, gigantic supercontinent called Pangaea. Imagine a world map where there are no separate continents, but rather one vast landmass stretching from pole to pole, surrounded by a single global ocean, Pantala. The climate on Pangaea was harsh. The interior regions, thousands of kilometers from the ocean, turned into deserts. There was almost no rain, and temperatures fluctuated from blistering heat during the day to freezing cold at night. But life flourished on the coasts. Forests of giant ferns and conifers grew there. Therapsids, the ancestors of mammals, roamed there, fanged and furred, but also egg-laying. The first reptiles, just learning to live far from water, crawled there. It was a world full of strange, transitional forms, a world poised between the ancient and the new. And then, at the end of the Permian period, 252 million years ago, a catastrophe began on Earth, the scale of which is unparalleled in the entire history of the planet. This event is known as the Great Dying, or the Permian Triassic Extinction. Some scientists simply call it the Great Death, and this name is justified. Because at the end of the Permian, 96% of all marine species and 70% of terrestrial vertebrate species perished. 96%. Think about it. If you counted 100 species of life in the ocean, only 4 would have survived the catastrophe. The other 96 would have disappeared forever. This was as close to the complete annihilation of life on Earth as you could possibly get without reaching it. What happened? What could have killed almost all life on the planet? For a long time, scientists couldn't answer this question. No traces of an asteroid strike were found. There was no ice age. The climate was warm, even hot. Where did all these species go? The answer came when geologists carefully studied the rocks in Siberia. There, over a vast area covering several million square kilometers, lies solidified lava, layer after layer kilometers thick. These are the Siberian Traps, one of the largest volcanic provinces on Earth. And this lava erupted precisely at the end of the Permian period, coinciding with the Great Dying. Coincidence? Nope. Cause and effect. But these weren't typical volcanic eruptions with a mountain, a crater, and a plume of ash. This was a fissure eruption. The Earth's crust cracked for hundreds of kilometers, and lava gushed out. Not an explosion, not a fountain, but a slow, unstoppable stream. The lava flowed for months, years, millennia. It flooded forests, swamps, and plains. Any living thing in its path was burned or suffocated. But the lava wasn't the biggest problem. The real problem was the gases that erupted from the Earth's depths along with it. The eruptions released monstrous volumes of carbon dioxide, sulfur dioxide, hydrogen chloride, and methane into the atmosphere. Carbon dioxide is a greenhouse gas. It traps heat. The more of it in the atmosphere, the warmer the planet. And at the end of the Permian, carbon dioxide concentrations skyrocketed. Temperatures began to rise. Not by a degree, not 2, but by 10 degrees across the entire planet. It could be even more. Imagine that the average temperature on Earth today is about 15 degrees. Now imagine it rising to 25. It wasn't just warming, it was turning the planet into an oven. But carbon dioxide works slowly over thousands of years. Sulfur dioxide, on the other hand, killed quickly. When sulfur enters the atmosphere, it combines with water vapor to form sulfuric acid. Clouds become acidic, and when it rains, it's acidic too. Imagine rain that burns your skin, kills plants, and corrodes rocks. Such rains fell over Pangaea in the first years of the eruptions. Forests began to die. Leaves turned black and fell, trees withered. The soil became acidic, and the bacteria and fungi that decompose organic matter died. Ecosystems collapsed from the bottom up. And underground, something even more terrifying was happening. Lava from the Siberian lava flows burned through layers of coal and oil buried in the Earth's crust. The coal caught fire. Imagine coal deposits burning underground, and the fire can't be extinguished. It burns for years, decades, maybe even centuries. Not only carbon dioxide and sulfur are released into the atmosphere, but also smoke, soot, ash, and toxic metals like mercury and lead. The sky turns gray, and the sun barely breaks through the smog. Surface temperatures fluctuate, hot during the day and cold at night, because smoke and ash block some of the sun's heat, but greenhouse gases still trap it in the atmosphere. The climate becomes chaotic and unpredictable. An equally terrible catastrophe was unfolding in the oceans. Carbon dioxide, entering the water, dissolves and forms carbonic acid. The ocean begins to acidify. This is called oceanic acidification. For organisms with calcareous shells and carapaces, this is fatal. The calcium that makes up their protective shells dissolves in the acidic water, like sugar in tea. Mollusks, corals, brachiopods, echinoderms, all of them began to die, without even understanding why. Their shells became thin, brittle, and cracked. Young individuals were unable to develop normally. Populations dwindled, then disappeared. But that's not all. When the ocean warms, warm water rises to the surface, while cold water remains at depth. Mixing slows, and oxygen stops reaching the bottom. And again, as in Devon, anoxia sets in. The ocean depths become dead zones. But in the Permian Ocean, anoxia was much worse, because in the anoxic water, specialized bacteria begin to thrive, bacteria that breathe sulfates rather than oxygen. They convert sulfates into hydrogen sulfide. Hydrogen sulfide is a poison, a gas with the smell of rotten eggs. In small concentrations, it's simply unpleasant, but in large concentrations, it's deadly. Hydrogen sulfide dissolves in water and poisons it. Fish try to escape anoxia, encounter hydrogen sulfide clouds, and die even faster. Then, hydrogen sulfide begins to escape from the water into the atmosphere. It rises into the air and kills land plants and animals on the coasts. Scientists have found geochemical traces of a massive hydrogen sulfide release in Permian rocks. This means the oceans weren't just dead, they were toxic. The water literally boiled with decomposing organic matter, and the air above it was poisoned. It was hell, a veritable hell on Earth. And it didn't last for days or months. It lasted for hundreds of thousands of years, maybe a million years. All this time, life on the planet slowly faded away. Paleontologists studying fossils from the late Permian observe a gradual unification of fauna. First, rare species disappear, then less common ones, then even common ones. At some point, almost no traces of life remain in the rocks. Only bacterial mats, slimy films of microorganisms that could survive in the acidic and noxic poison water. These mats are called stromatolites, and they are similar to those that existed on Earth 3 billion years ago, when life was just beginning. It turns out that the Great Dying set the planet back billions of years of evolution. Complex ecosystems disappeared, leaving only the most primitive life forms. How anything could have survived in such conditions remains a mystery. Scientists speculate that salvation came from small refuges. Perhaps somewhere in the mountains, at higher altitudes where the air was cleaner, pockets of life survived. Perhaps in deep caves where the poisonous gas didn't reach. Perhaps in the polar regions where it was colder and the ocean still retained a little oxygen. Small populations of organisms, just a few thousand or even hundreds of individuals, could survive there. And these tiny populations became the seeds for life's resurgence. But the resurgence was incredibly slow. Typically, after a mass extinction, the biosphere recovers within a few million years. New species evolve from the survivors, fill empty niches, and create new ecosystems. But after the Great Dying, recovery took almost 10 million years. This is the longest recovery in the history of the planet. Why did it take so long? Because conditions remained poor long after the eruptions ceased. The climate was unstable, the oceans were still partially anoxic, and the water's acidity declined slowly. Life had to not only recover, but evolve anew, adapting to entirely new, harsher conditions. The Great Dying left a deep scar on Earth's history. Entire groups of organisms that dominated the Paleozoic era disappeared forever. Trilobites, which had existed for 300 million years and survived 2 previous catastrophes, became completely extinct. Large therapsids, which could have been the ancestors of mammals, almost completely disappeared, with only smaller forms surviving. But reptiles, which had previously played a secondary role, were given a chance. The surviving reptiles gave rise to dinosaurs, who became the rulers of the Mesozoic era. But that's another story. What can we learn from the Permian catastrophe? First, that the planet is capable of self-destruction. Volcanoes, underground fires, and gas emissions are all natural processes, but at a critical moment, they can converge in such a way that the results are catastrophic. Secondly, the greenhouse effect is a real threat. Carbon dioxide released into the atmosphere can heat the planet to a temperature incompatible with most forms of life. Third, that the oceans are not a bottomless reservoir that can absorb any pollution. They are vulnerable, and when they die, so does life on land because everything is connected. And finally, that survival in a moment of disaster is a matter of luck, not strength or intelligence. The strongest, the most adaptable, the most successful species died out just like the rest. Those who were simply lucky survived. The Triassic period began after the Great Dying, in a world devastated and scarred. Life slowly recovered, and by the middle of the Triassic, the planet was once again teeming with diversity. The first dinosaurs, small, agile predators, and herbivores appeared. The first true mammals appeared, tiny, mouse-sized creatures that hid from daytime predators and hunted at night. Ichthyosaurs, dolphin-like reptiles, and long-necked plesiosaurs swam the oceans. The Triassic world was strange and diverse, full of evolutionary experiments. And it seemed that after the Permian hell, Earth had finally found stability. But that wasn't the case. 201 million years ago, at the very end of the Triassic, the planet was struck by another catastrophe. It wasn't as devastating as the Permian, but it still killed off about 70% of all species. Once again, volcanoes were the cause. This time, the Central Atlantic igneous province erupted. Pangea began to split apart. North America separated from Africa, and a new ocean, the Atlantic, was born between them. This process was accompanied by massive eruptions. Lava flooded the territories of what would become Brazil, West Africa, and North America. The lava fields were vast, several million square kilometers. Once again, carbon dioxide and sulfur poured into the atmosphere. But the Triassic extinction differed from the Permian in one important detail. The climate changed not gradually, but in leaps and bounds. Initially, the eruptions released sulfur, which formed aerosols in the upper atmosphere. These aerosols reflected sunlight, causing temperatures to drop. A volcanic winter was approaching. The cold lasted for several years, perhaps decades. Plants stopped growing, herbivores starved to death, and predators followed suit. Then the sulfur would settle out of the atmosphere, fall with rain, and its effect would cease. But carbon dioxide remained. It accumulated in the atmosphere, and warming began. Temperatures rose sharply. The climate became hot and humid. Organisms that had adapted to the cold were suddenly confronted with intense heat. Then another eruption, another burst of sulfur, and the cycle repeated. These climate swings were deadly. Evolution can't keep up with such rapid change. Species adapted to one environment become extinct when conditions change. And when conditions change again, those who have adapted to the new conditions die out. Ultimately, only those who can quickly adapt to change and have a broad tolerance range survive. But such species are few. Most are specialized, adapted to specific conditions. And when those conditions disappear, they disappear too. Paleontologists see the same signs of disaster in Triassic rocks as in Permian ones. Mass extinctions of marine organisms, the disappearance of coral reefs, and the spread of anoxic zones in the oceans. But on land, the picture was slightly different. The large tetrapods that dominated the early and middle Triassic became almost completely extinct. Among them were archosaurs, the ancestors of dinosaurs and crocodiles, and theropods, large predators. But the smaller dinosaurs survived. And after the catastrophe, they were presented with an opportunity they hadn't had before: empty ecological niches. Competitors died out, predators disappeared, and dinosaurs began to grow, evolve, and diversify. Over the next few million years, they filled all available niches and became the dominant group of terrestrial vertebrates for the next 150 million years. Thus, the Triassic extinction event cleared the way for the age of dinosaurs. Without this catastrophe, dinosaurs might have remained small, secondary creatures. But the disaster wiped out their competitors, and they took over. This is another lesson from mass extinctions. They create opportunities. Yes, they kill most. But the few who survive are granted a world with few competitors and abundant resources. And these few become the founders of new dynasties. The Triassic extinction also demonstrated that climate instability can be just as dangerous as extreme conditions. Life can adapt to cold or heat if they're constant. But when temperatures fluctuate wildly, adaptation becomes impossible. It's like being forced to live in the Arctic and then the Sahara, switching locations every few years. You wouldn't have time to dress warmly or undress. You'd simply die of stress. This is how species died out at the end of the Triassic. The Triassic catastrophe was followed by the Jurassic period, the golden age of dinosaurs. And then the Malovian period, when dinosaurs reached their peak diversity and size. And at the end of the Million period, 66 million years ago, another mass extinction occurred, the one that killed off the dinosaurs. But we know more about this one than the others because we discovered an asteroid impact crater. This wasn't a volcanic eruption, not a climate change, but a single instantaneous impact from space. An asteroid approximately 10 kilometers in diameter slammed into Earth near what is now Yucatan, Mexico. The explosion was billions of times more powerful than all the nuclear bombs ever created. The shock wave rippled across the planet, triggering a tsunami hundreds of meters high and lifting trillions of tons of dust and debris into the air. The sky turned black, the sun disappeared, photosynthesis stopped, and plants began to die. Deprived of food, herbivorous dinosaurs died out within months or years. The predators that hunted the herbivores followed them. Only small creatures capable of feeding on seeds, insects, and carrion survived this catastrophe. Among them were mammals, which had previously lived in the shadow of the dinosaurs. After the dinosaurs' extinction, mammals began to evolve, occupying the vacated niches, and ultimately gave rise to all modern groups, including primates and, ultimately, us. So we humans only exist because the dinosaurs died out. If it hadn't been for that asteroid, if it had missed us or fallen into the ocean far from land, dinosaurs would have continued to dominate, and mammals would have remained small, inconspicuous creatures. There would have been no primates, no monkeys, no humans. Our existence is the result of a catastrophe that killed millions of other species. It's a disturbing thought. We live on the bones of those who didn't survive. Now that we've examined the 5 great extinctions, we can try to find patterns in them. Scientists have long searched for a common cause or pattern uniting these catastrophes. And in recent years, an interesting theory has emerged. It turns out that almost all mass extinctions are associated with a sharp change in global temperature, either cooling or warming, but always rapid and significant. Researchers analyzed data on ancient climates reconstructed from isotopes in fossils and rocks and discovered a kind of death formula. If Earth's average temperature drops by 7 degrees Celsius or more, a mass extinction begins. If it rises by 9 degrees or more, the same thing happens. These aren't random numbers. They're thresholds beyond which most ecosystems can no longer function. A 7-degree cooling is enough to trigger glaciation, cause sea levels to fall, and cause ocean currents to slow or stop. 9 degrees of warming is enough to warm the oceans to the point of anaxia, turn tropical forests into deserts, and melt polar ice caps and flood coastal areas. These thresholds are not absolute. The rate of change also matters. If temperatures change slowly over millions of years, life has time to adapt. Species migrate, evolve, and adapt. But if changes occur over tens or hundreds of thousands of years, adaptation becomes impossible. This is precisely what happened during the Great Dyings. Temperatures were changing too rapidly. And here we come to the most alarming point. Today, in the 21st century, the Earth's average temperature is rising. Since the Industrial Revolution began in the mid-19th century, it has risen by about 1 degree. That doesn't sound terrible. 1 degree seems like a small change, but this change occurred in just 150 years, which is a blink of an eye in geological time. And it continues. According to current forecasts, if humanity doesn't take radical measures to reduce greenhouse gas emissions, temperatures could rise by another 3 to 4 degrees by the end of the 21st century. And by the end of the 22nd or 23rd century, by 7, 8, and maybe even 9 degrees. We are approaching the upper limit of the death equation. Of course, there's a big difference between natural climate change in the past and what's happening now. In the past, changes were caused by volcanoes, asteroids, and continental drift. Now, changes are driven by the actions of single species, us, humans. We burn fossil fuels, coal, oil, and gas that took millions of years to form. We release carbon dioxide, which was locked in the Earth's crust, into the atmosphere. We cut down forests that absorb this carbon dioxide. We are creating a greenhouse effect with our own hands. And this greenhouse effect is already beginning to change the planet. Glaciers are melting, Sea levels are rising, and extreme weather events are becoming more frequent and destructive. Coral reefs that have existed for millions of years are beginning to bleach and die due to rising water temperatures. Species are dying out at an unprecedented rate. Scientists are calling this the sixth mass extinction, and it has already begun. We're living in it right now. But there are differences from past extinctions. In the past, no species could stop a catastrophe. Dinosaurs couldn't prevent an asteroid strike. Trilobites couldn't stop volcanoes. They were helpless victims of the elements. For the first time in the history of the planet, we have the power to stop extinction, or at least slow it down. We have the technologies to transition to renewable energy sources: solar, wind, hydro. We have the knowledge to restore ecosystems and protect species. We have time. Not much, but we have it. Calculations show that if we stabilize greenhouse gas emissions in the coming decades, temperatures will not reach the critical threshold of 9 degrees by 2500. We can maintain a safe level. But to do so, we need to act. Don't delay. Don't rely on someone else to solve the problem. Every degree of warming makes recovery more difficult. Every extinct species is an irreparable loss. Every destroyed habitat is a blow to the sustainability of the biosphere. We stand at the threshold of a choice: continue down the path that leads to disaster or turn away from it. And this choice must be made now. Earth's history teaches us that catastrophes are real, that they happen, that they kill almost all life. But it also teaches us that life is resilient, that even after the most terrible blows it recovers, that there are always survivors who give rise to new forms. We are the descendants of these survivors. Our genes are encoded with the experience of billions of years of evolution, the experience of overcoming catastrophes. We know how to survive. But for the first time, we can do more than just survive. We can prevent catastrophe. We can prevent the sixth extinction, or at least make it less devastating. This is our responsibility, not to the planet. The planet will survive without us, just as it survived all the previous catastrophes, but to ourselves and to all the other species with which we share this world. When you look at green forests, at oceans, at the diversity of life around you, remember that all of this is the result of billions of years of struggle. Every tree, every animal, every microorganism is a descendant of those who survived ice ages, volcanic winters, acidic oceans, asteroid impacts. Life has been through hell and back, and it deserves our respect and our protection. The Earth has died 5 times. 5 times life on it nearly disappeared. 5 times it recovered, becoming stronger, more diverse, more complex. Now, the sixth extinction is beginning. But this time we have our finger on the button. We can press it and hasten the catastrophe, or we can let go and give life a chance. The choice is ours, and history will judge us by our choices. If you enjoyed this story of survival and disaster, please support the channel with a like and subscribe so you don't miss other videos about our amazing and fragile planet. Thank you for being with us until the end.